Good morning all. So far we have discussed the basic probability concepts. Then we discussed capacity outage table. And finally we have discussed loss of load indices. Today is the last class for module 1 where we are going to discuss loss of energy indices. The standard LOEE approach utilizes the peak load variation curve or individual peak loads to calculate the expected number of days in the period that the daily peak load exceeds the available installed capacity. So what does it mean? That loss of load is basically when generation model is combined with or convolved with the load model. Now this LOEE index can be obtained in two ways. One is use individual hourly values, number of peak loads in a year. It can be daily values also, as we have seen, or it can be load duration curve, percentage of load equaled or exceeded. The area under the load duration curve represents the energy utilized during the specified period and can be used to calculate the expected energy not supplied due to insufficient installed capacity. So while calculating loss of energy indices, our objective is to obtain how much energy is not supplied. Load duration curve is simply the variation of load with time. Now when we integrate that curve, we get the area under it, which is basically load into time or megawatt into hour, megawatt hour. The probability of having varying amounts of capacity unavailable are combined with the system load. So what we do? We have the capacity outage table, we combine with the system load. Although the loss of energy approach has more physical significance than loss of load approach, it is not as flexible in overall application. See, what matters is how much energy is not supplied, not exactly the load not supplied. Okay, but then it is not that flexible, just like loss of load part, because loss of load can be obtained by directly convolving the capacity outage table with the load curve. It should be noted that electrical power systems are generally energy limited than power or capacity limited. Okay, it means that how much energy the system can supply. Okay, not how much peak load. This is important, but it is mostly the energy that we are concerned about in million units. Okay, this curve is again from the Billington book. So we have seen this curve. So this is the load duration curve. Okay, this is the load duration curve. So it is plotted between the load on the y-axis and percentage of time load exceeded the indicated value on the x-axis, and this corresponding to this point, this line gives you the base load. Now if this much capacity outage occurs, then beyond this only capacity outage will occur, right? Or sorry, loss of load will occur. But after this, there is no loss of load. Okay, so here OK is the magnitude of capacity outage, PK is the probability of that capacity outage, EK is the energy curtailed due to that capacity outage. Okay. Now these are the very important formulas. The probability of energy curtailed is EK into probability of load outage. Okay, so how much energy is curtailed because of a particular load outage is to be multiplied with PK. And we can compute the loss of energy expectations as the summation of all these products. Okay, in per units you can simply divide by energy. Now another unit known as the energy index of reliability is obtained by 1 minus LOE per unit. Okay. Now this is the problem that we are going to consider. So consider a system containing 540 megawatt units, each with a forced outage rate of 0.01. The system peak load is shown below. The study period is assumed to be a year and the 100% abscissa corresponds to 365 days. So this 100% percentage of daily peak load exceeded the indicated value. This is 365 days. Okay. So we need to compute the loss of energy expectations in per units and the energy index of reliability, that is 1 minus LOLE per unit. So we'll go to the Excel for this and find out the solution. Okay. So if you can see here, this is LOEE. Okay. So we have got 540 megawatt units, as you can see here, 40 into 5, 200 megawatts. The peak load here is 160 megawatt. And this particular part is to know how much time load is equaled or exceeded. Okay. So first you have to compute the capacity outage table. As you know, total units 5, FOR is 0.01. So we start with units out 0, 1, 2, 3, 4. If the units out is 0, capacity outage is 0 megawatt. If the unit out is 1, capacity outage is 40 megawatt. If the units out is 2, capacity outage is 80 megawatt. If the units out is 3, capacity outage is 120 megawatt. If the units out is 4, the capacity outage is 160 megawatt. Now, total megawatt available is installed capacity 200, which is D8, as you can see here, D8 is 200 minus the capacity outage, which is I8. So D8 minus I8. Now D8 should be fixed because the installed capacity is fixed. So if you subtract the capacity outage from the total megawatt available or total megawatt capacity, then we get the megawatt available, which varies between 200 megawatt, 160, 120, 80 and 40. Now this individual probability, as you know, it can be used directly using the binomial distribution. So capacity outage table is formed, and we are mostly concerned about the cumulative reliability, okay, which is computed in a reverse way. Now you see here this part, total time and for which what is the energy loss, that can be computed from that particular curve. Okay. Now this total time we have already seen while we did LOEE, LOLE, loss of load expectation. Now only we have to know how this total energy lost, total energy which could not be made, that can be computed. So this we will again go to the PPT and see there. Okay. But before that, understand that, so this is the only part that we have not yet seen how it is obtained. So this one we will again go to the PPT and see there. Now this is the direct application of the formula, summation EK into PK. So what is EK? EK is the total energy not supplied into what is the probability. PK, as you see, is in the individual probability will be computed here because that is the individual probability. So it is K10 into N10. So the individual probability of outage into N10, the energy outage. Okay, K10 into N10. Okay, so K10 into N10 will be, as you see here, K10 into N10. So this is the energy loss probability, LOEE. Okay, so this is the LOE, energy loss probability is this one, K, column K. So when we add that up, we get this term, the 0.033350059 as the LOEE, loss of energy expectations. Now this is the loss of energy expectation. As you know, when you divide by the total capacity, then we get the LOEE in per unit. So where from that is obtained? That is obtained from N18. So as you see here, N18 is the total energy which is under the load duration curve. Okay. So as you see here, this is 0.4, 0.6. This is obtained from the curve itself. So we'll see that. Okay. So B14 into 0.4, 0.5 into this is half. This second term is basically half of that triangle, half into base into height, and the first one is the area of the rectangle. Okay, B14 into 0.4. Okay. Now EIR is 1 minus the energy index of reliability, which is N16. Okay. So this is how in the Excel I have demonstrated how the loss of energy expectations is calculated. Now what remains to be seen is how these two particular energy terms, the loss of energy terms, are calculated. So we'll go to the Excel sheet again, PDF again. Okay. So this is how in this slide it is shown how the expected energy not supplied is calculated. So if you see here, total time is 0, 20, 100%. Now no, this one is for okay, we'll see here. We'll go to the Excel sheet, okay, and we'll go to this particular curve, okay, this particular curve. Now what is the expected energy not supplied for a particular duration? What is the total area? The total area is, as we have seen, the total area is 160. Okay, 160. Here 100%, see it is 0%, 40%, 100% in the y-axis. So 100% means the peak load, which is given to be 160 megawatt. Okay, so first we will calculate this triangle area. What is this triangle area? This is from 40% load, peak load, to 100% peak load. 100 peak load is 160 megawatt. 40% peak load will be 0.4 into 160. So it will be 64 megawatts. Okay. So what is that particular area? So that will be 160 into 0.4 into, this is 100%, this area. Okay. So there are two areas, 0 to 40. So it is 0.4 of 160 megawatt. So this is that side into 1. So that means it will be 160 into 0.4 into 1. So this is the energy not supplied here, and for this triangular part it will be half into 1, which is the base, into 0.6 into 160, because this is 40%, so this part will be 60%. So to make it clear, I'll go again to the Excel sheet. Okay, so this is the Excel sheet. So as you see here, I have told you what is this total area, 112. This is equal to B14 into 0.4, 160 into 0.4, 0.5, half into 160 into 0.6 into 1 is not multiplied because there is 100% in the abscissa. Okay. Now how this is 0.417? So 0.417 is obtained from here. Okay, 0.417 is obtained from here, from the load duration curve based on So we are considering various load loss scenarios. Okay, so as you can see here, megawatt available is 200. So 200 megawatt available, we are not bothered about, no loss of load occurs. 160 megawatt is the peak load. Okay, so until 160 megawatt is available, there is no loss of load. Now when 120 megawatt is available, there is a certain loss of load. Okay, so what is the loss of load and hence the corresponding energy? So the loss of load will be, for only 41.7%. Okay, so we have to see this from the curve as we saw in the last class. Okay, so we have to get 120 megawatt on the abscissa, then we have to find out the corresponding time from the, we have to get 120 megawatt in the ordinate, and then we have to get the corresponding time in the abscissa, which is 41.7%. Okay, this we have seen in the last class. So refer to the last class if you want to understand this. Similarly, we'll take 80 megawatt in the ordinate or y-axis and get the corresponding time in the x-axis, which is 83.4%. It simply means that for 83.4% of the time, the megawatt available is, for 83.4% of the time, the peak load is, for 83.4% of the, okay, we'll see this in the curve, 41.7% and 83.4%. Okay, so we'll go to the curve again. So if you see here, so 83.4% should be somewhere here. Okay, so for 83.4%, the load will be here, this one. So that is around 80 megawatt. Okay, this one, this load is around 80 megawatt, I think, because total 100% is 160, 40% is 64, so 80 will be somewhere here. So that is 83% of the time. So 83% of the time load exceeds 80 megawatt. So if there is a capacity outage more than 80 megawatt, then there will be loss of load. Similarly, what will be the other case? The other case was regarding 120 megawatt. Okay, so we have to see for how much time the 120 megawatt load is available. So 120 means it will be somewhere, 100% is 160, so somewhere here the 120 megawatt load will be there. So if you draw a line here, then you have to find out the percentage by using the concept of similarity of triangles, and you will get 41.7% here. Okay, got it? Okay, now again we'll go to the Excel sheet. Okay, so this one I was discussing there, for 41.7% of the time the load is 120 megawatt or more. For 83.4% of the time the load is 80 megawatt or more. Therefore, in both the cases, in respective cases, if the load is 120 megawatt or more, there will be loss of load. In this case, if the outage is 120 megawatt or more, or the available capacity is 80 megawatt, less than 80 megawatt, then there will be loss of load. Okay, okay. So this is how the LOEE is calculated. So now we'll go and complete the rest of the slide. Okay, now this corresponds to question number 4. Okay, so what is the corresponding problem set? So we'll go to the problem set and see here. So we have completed prerequisites. In module 1, we are now concerned about LOEE, the loss of energy indices, which is this one. Okay, question number 4. For the 5 into 40 megawatt system, compute the LOEE per unit and energy index of reliability. So this is what is important. Okay, this will complete what is required for loss of energy indices. Now there is one more problem on this, which is a further extension problem. So this you can take as an homework to complete it, but we will just discuss the essence of this problem. Okay, so what is this problem? It says consider the load duration curve shown in figure 2.2. This is a different kind of load duration curve for a period of 100 hours. Okay, so the total duration is 100 hours, not 100%. And the generating unit capacity data is given in table 2.3. So this is the generating unit data. So unit 1, you can have various capacity and the corresponding probability. Unit 2, various capacity and the corresponding probability. Unit 3, the various capacity and the corresponding probability. Okay, so assume that the economic loading order is unit 1 is first reference, then unit 2, then unit 3. Compute total energy required in this period ENS 0, compute ENS 2 for the unit 1 and 2 combined, compute ENS 3 for loads for the units 1, 2, 3 and 3 combined. Okay, and compute the expected energy produced by the units 1, 2 and 3. Okay, so we just make this term because there are 2 generators, there are 3 generators. Okay, so now we'll have we'll go to the PPT and find out and see. Yes. So this is how the expected energy not supplied ENS 0 will be calculated. I have explained it. You have to find out the areas of various curves. So total area under the load duration curve will be expected energy not supplied if there were no units in the system. So that is EENS 0. Then we will go to total 2 units in the system and total 3 units in the system. Got it? So this is the problem. So the answer is with unit 1 with no units, ENS with, okay, unit 1, that was not there in the question. So with unit 1 only, so this is the total energy requirement, okay, or not supplied. ENS2 is this, ENS3 come with 1 unit, with 2 units, with 3 units. So the real solution will be available in the Excel sheet. Okay. Okay, somehow I could not find the solution here, so I will supply it later if required. Okay, you refer to this Excel sheet to compute the understand the basics of loss of energy outage indices calculated, loss of energy expectations calculation. Okay, and compute this manually. Okay, next we will discuss something known as the energy limited systems. The simplest energy limited situation is to incorporate into analysis is the condition in which the output capacity of a unit is dictated by the energy available. Okay, an example is a run of the river hydro installation with little or no storage. The flow rate determines the unit output capacity, which is then represented as a multi-state unit. Generating units having short-term storage associated with the prime mover can be used to peak shave the load and therefore reduce the requirement from most expensive units, which can start very fast. Okay, the first step is to capacity modify the load duration curve using a conditional probability approach based on this peak shaving. The modified curve is the equivalent load curve for the rest of the units if the units used to modify it was first in the priority list. The capacity modified curve is then energy modified using the energy probability distribution of the unit under considerations for energy limited systems like run of river hydro installations. Okay, this is one approach. We are not going to the details of this. It's only for your information. Okay, so that completes the energy loss of energy expectations. Now we'll come to this question which I have left. This is question number 5. Okay, this is the question. This is question number 4. This is question number 5. So I told you that it is not available. It is available in the Excel, but I found out that it is available as a PDF. Okay, so I'll open that. Okay, this is the solution. So here, okay, so here basic things about LOEE is given with the formulas that I have given you, and this is, and for that explicit formula. Okay, now this one is the question number 5. So this, how this calculation is made is given here. Okay, how ENS, ENS1, ENS2 are calculated. Okay, so how these are calculated, this is provided here. Rather than the Excel sheet, this is provided here. Okay, so go through it to solve that problem. So we'll stop here. Thank you for listening.